analysis and concepts. And believe it or not, signal integrity is all around us. It's happening right now. It's happening at this moment. We have a transmitter, which is me, and you guys, the receivers. And between us, there's a long channel. If there's something were to go back in the channel, we have a signal integrity problem. But today was focused mainly on the signal integrity in digital communication channels, where we have a CPU going to an LED display, and in between, there are all these interconnects. And like the SI guru would say, which is my PhD advisor would say, signal integrity is about the problems interconnects introduce and how to avoid them. Well, to do that, we'll learn signal integrity through a case study, the case of a failing channel. We will apply the three-step to solve this problem. The three-step approach is we simulate the channel first, we'll find the root cause of degradation, and finally we'll explore design solutions. In the process, we will learn the essential signal integrity analyses, such as eye diagram, mixed mode S parameters, time domain reflectometry, and single pulse response. And finally, I will give you some PCIe Express pre-layout application example, and what we have in our new software is a back-channel auto negotiation interface. Going straight to it, we'll first simulate the channel. Right here, we'll use eye diagram simulation to evaluate the differential channel in the middle in hand. On the transmitter side, we'll see the eye is open. What does that mean? That means a digital 1 and 0 can be clearly distinguished. But after it goes to the channel, the eye is closed. The receiver cannot tell whether it's a 1 or a 0 anymore. Well, how do we generate eye diagrams? The process is like this. We will start with PRBS, which stands for pseudo-random binary sequence. By setting this, we'll be able to slowly generate it. Okay, once we send this PRBS in there, we will use our knowledge of unit intervals. We'll group 2 UI at a time, another 2 UI, and another 2 UI. We'll slice these together. And by combining these slices, first slice, second slice, and third slice, we can combine them into an eye. And you can imagine if we've placed enough slices together, it will look much better. Now, what do we discuss so far? So far, we have a closed eye at the receiver. After using PRBS as a transmitter, an open eye, and going through the channel, the eye is closed. So that leads us to the second step of the three-step process. We need to find the root cause of the degradation. And to do so, we'll use S parameter. And here's a quick overview of S parameter. Say you have the channel in the middle, and you're sending a sine wave at frequency f0. S11 will tell you what's coming back. It's also known as the reflection coefficient and the return loss. If you're coming from a microwave engineering background, you might be quoting return loss as a positive number. But in signal integrity, we embrace this ambiguity where we can also quote return loss as a negative number. Similarly, if we're looking at port 2 instead of port 1, you will see S21, which is the port 2 excited by port 1. It's also known as the transmission coefficient and the insertion loss. Likewise, the convention in SI, signal integrity, is such that you can quote insertion loss as a positive number or negative number in dB. We will understand. Well, since you're designing in PCI Express, it's going to be in differential lines. So of course, we have to use 2 lines to make a differential pair. In these 2 lines, we'll be sending differential signal from differential port 1 to differential port 2. And what's underneath this, the two lines together becomes a mixed mode S parameters, where we're describing how differential signal and common signal interact and create one another. Here's a quick look of what a mixed mode S parameter matrix would look like. Starting out from the outside is we have different stimuluses. We have differential signal, we have common signal, stimulus, on the top hand side. And on the left is the responses. And we have 4 quadrants of very distinctive behaviors. On the top left is the differential input, creating differential output, and so on. Now this might seem really intimidating at first because we have 4 times 4, that's 16 S parameters, and they're complex, so you have to multiply by 2, so that's many numbers. The key is not to get lost in all these data. There are a couple key data that we look at, key S parameters, especially SDD11. To make sure the nomenclature is clear, the DD color, the first D color in blue is a differential response, and the first blue number 1 is a response at port 1, excited by the red differential input at port 1. And other than SDD11, which is also the differential return loss, we have differential insertion loss as well. And when we are talking about differential pairs, we have to talk about mode conversion, where the asymmetry in your lines are driving your interconnect differently, even and odd mode. And SDC21, where a differential signal is generated by the common signal. Great. Now we're going to use S parameter, but like Eric would say, we have to apply rule number 9. What do we expect with a given channel? To do that, we'll have to ask ourselves, what do we expect to see in SDD11 and SDD21? And here's a table of the information that we need. And we'll take step-by-step approach to figure out what we expect. First, we'll take a quick glimpse at the virtual channel. On the top, we have a 3-inch microstrip differential pair. In the middle is a differential via structure. And finally, we're transitioning into a 3-inch strip line differential pair. Here's a cross-section of the first section, microstrip differential pair. I've outlined the width of the trace, and they're about 14 mils. Given the rule of thumb, if we look at it single-endedly, the width is 14 mils and the substrate height is 7 mils. Well, we will expect in FR4 environment, the impedance is about 50 ohms. But now since we're a differential pair, and they are far enough apart, so we can just multiply by 2. Now the tricky part is we have solder mask on top. That means it's going to lower the impedance a little bit. So here we'll expect the differential impedance of this cross-section to be a little less than 100 ohms. Next, we'll look at the strip line differential pair. Similarly, we'll use our rule of thumb approximation, where if the line width is about the width over height of the substrate is between 0.8 to 1, then the single-ended impedance is about 50 ohms. And again, they are a little far apart. They're 3 times the line width apart. That means we can just multiply by 2. None of the field lines interfere with each other. And we expect the impedance to be about 100 ohms. Great. Now we have filling the bottom 2 items. Let's see what we expect the SDD11 and SDD21 would look like. But before that, we'll also take a look at the loss for SDD21. Now I'm running at a data rate at 32 gigabit per second. Divided that by 2 gives us a Nyquist frequency at 16 gigahertz. Estimating the loss at 0.1 dB per inch per gigahertz, I should expect the 3-inch microstrip to be 16 multiplied by 0.1 multiplied by 3, which is about 4.8 dB. And also the 3-inch strip line. I call it 5, give or take. The next, for the via, well, I'm going to assume that it's a well-designed via. It has small loss. And the impedance is also a little unknown, but we'll think it's okay. Since it's small, it won't make a big impact. Now we'll take a look at our expectation and the some S parameter results. Our expectation for the SDD11, because we expect the impedance to be close to 100 ohms, we'll expect a really low dB value for the SDD11 on the left-hand side, as we can see. And for the SDD21, because the dielectric loss and conductor loss, we'll expect almost a linear drop-off, and we'll expect negative 10 dB at the Nyquist frequency, 16 gigahertz. Yes, the 10 dB is 5 plus 5, which is the two microstrip lumped together. Let's see what the S parameter shows us. The differential return loss is a little different than what we expect. It did start at negative 30, but it went up to negative 10, which we didn't expect. Now let's take a look at the differential insertion loss. Wow. That is different. That is not what we expect. We expect a linear behavior, but instead we get a dip in the middle. Where's that what's happening? Let's take a look at the channel again. We have a microstrip differential pair, a via structure, and another differential pair. Well, there are two differential pairs together. You know, I'm just gonna remove that via and simulate only the transmission lines and see if that's the linear relationship that we expect. And of course, when I simulated the transmission line only, I'm getting at 16 gigahertz on Nyquist about minus 10 dB. But when the via is included, there is a dip. That tells me the via is possibly the problem, and we'll need to take a closer look at the via because of the dip. Now let's take a closer at the differential via. Since they're differential and they're far enough apart, I'm gonna explode it and look at the middle part. And I could do a quick measurement, and the middle part is about 75 mils. Given my data rate and my Nyquist, I multiply by 5 to get the bandwidth and compute the wavelength. It turns out the wavelength is 75 mils, which will fit in that stub. And when a wavelength fits in the physical length, when the voltage and the current wave can fit in a physical length, and it's varying with the physical length, that's the definition of a transmission line as defined on the bottom right-hand corner. So in order to understand this dip behavior, we have to understand transmission line. Well, what's so special about the transmission line is the reflection that it's going to create when the wave sees impedance discontinuity in the transmission line. On the left-hand corner, you can see the top view of a structure. If there's a wave coming down through impedance Z1 that is 15 ohms, and another one, Z2, that we don't know, it's coming down, there is a impedance discontinuity. It's going to be reflected after seeing this reflection coefficient gamma. And the reflection coefficient gamma is defined as the second guy, Z2, minus the first guy, Z1, divided by the sum. Well, there are different numbers, but it ranges from -1 to 1. Here's the range of numbers we can see. Well, you might be thinking, well, great, there's reflection, so what? Why do we care? The key of the reflection is it gives the wave a different wave to approach at the exit. Say if we were trying to transmit from the left of the T to the black arrow. Of course, there's a straightforward way going straight, but there's another way. Given the reflection, the wave can travel back down through this blue/teal arrow, get reflected, and get back to the black arrow. And let's take a look at how that's going to work. First, the straightforward path is again straightforward, right? But then I'll put a black dot there for record keeping. Now let's take a look at the reflected wave. It's going to travel down this path, in the stop direction. And when the frequency is such that the length, the physical length of the stub is a quarter of a wavelength. The wave is going to travel down, see an open, which gives us gamma 1, get reflected back. And since it's twice of the lambda over 4, it's going to have a delay of lambda over 2. And what does it look at the black arrow? It looks like this. And the black dot is there showing the delay. Adding that to what we already have from the red straightforward path, we can see that it is a destructive interference. This is what we call a quarter wave stop resonance, where if the length is a quarter of a wavelength, then on the output side, it seems like nothing has been transmitted. It's a virtual short. Well, where were we when we started this conversation? We're looking at the stub, and we said stub is about 75 mils. And we can put that right back to our model. If the length of the stub is 75 mils, we can do a little math. We can do a little calculations here, and given the speed in FR4, velocity is 6 inch per nanosecond, we can quickly calculate the resonant frequency of that stub, which is 1.5 divided by the length in inches. After the calculation, we can expect the resonant frequency of this particular stub to be at 20 gigahertz. Let's see what the differential looks like. Similar. Then bam. Once we do a 3D full wave analysis in our VER designer, we can see that it's very close. The simulated and our rule of thumb approximation are really close. We have a good engineering intuition, and we know that the stub is a possible root cause of a degradation. And our reasoning is that the stub between the 3-inch microstrip and the strip line differential pair is giving us a closed eye because of this dip that is taking out all the frequency content around that area, around that frequency. Now remember I said possible. We'll do another consistency test to make sure that we know it is the root cause. To do so, we will use TDR, the time domain reflectometry impedance plot. And here's how we're gonna, theoretically how we approach it. We have a channel under test. I'm going to leave the right-hand side open, as we can see on the right-hand corner. Or we're looking at impedance, and I will write impedance expression here. It's the reference impedance Z naught times 1 plus gamma over T divided by 1 minus gamma of T. Again, gamma is a reflection coefficient. But right now we do not have the gamma. We'll need to have a step generator, a reflection monitor, to calculate the gamma. As the step generator shoots an incident wave to the channel and get reflected by the channel, all these incident wave and reflected wave will be recorded by the reflection monitor. And after we have the reflected signal and the incident signal, we will be able to calculate the gamma and find the impedance. What do we expect? Same deal. We will have to apply rule number 9. Here, estimated delay is 6 inch per nanosecond, and we have on the bottom 3-inch microstrip. I would expect it to have a round trip delay of 1 nanosecond, because since we're doing reflectometry, we'll have to wait for it to reflect back. That is 3 times 2, the round trip is 6 inches, divided by 6, that's 1 nanosecond. Now here's the profile on top of what we just discussed with impedance. It's going to look a little like this. Again, for record keeping purposes, I'm going to have an ideal 100 ohms. In the front, about 0.5 nanosecond round trip time. And here is our microstrip. In the middle, we are not sure what the VIA looks like. And again, we're going through the strip line and the open. The open is there to make sure that we know where our channel ends. Now let's take a look at the VIA. What do we expect the VIA to have impedance-wise? If we look from the VIA perspective, we're seeing this kind of schematic. We have a differential via impedance going through a differential strip line feed in the stub. Now, in the perfect world, I'm going to assume they're both 100 ohms. Perfectly designed differential impedance, 100 ohms, and the stub is 100 ohms. Given that, looking at the black from the red arrow perspective, it's a parallel combination between the two. So I would expect the parallel combination to be about 50 ohms. The rule of, well, it's just a general estimation. And let's see how well our estimation is to the real thing. After performing our TDR, we can see that, well, it's not really 50 ohms, but it's lower, which is, what we expect. It's not higher, but it's closer to 50. And we made a great assumption there is 100 ohms. So this is consistent. Now we're really sure the stub is the root cause of the eye closure. A little quick summary. We saw a closed eye, and we looked at the stub. We identified the stub to be the root cause, the possible root cause. Then we make sure we have consistency tests to double check that, and now we're sure the root cause is the via stub. So far, we have completed number 1 and number 2. We'll go on to number 3, explore design solutions. And to do so, the very first way is, of course, if the stub is the problem, let's remove it. We remove the stub with back drilling. Usually, back drilling is done in industry. Although you have to pay a little extra, sometimes it's worthwhile if you do have the money. And we can also do back drilling in the virtual world. We'll be able to take out the via just like that. And of course, after the problem, the root cause is being solved, we can expect the eye to be more open. And here it is. The eye is more open already. Solution number 2. What if we add equalization? The eye is now closed, and what equalization is doing in a frequency domain is to unify all the frequency spectrums. Okay, it can be also done in the time domain. And here what we'll look at is decision feedback equalization, where the decision is made, then feedback to a summer in a digital computation is done to equalize the channel. And now the question is, well, I can do DFE, decision feedback equalization, but how many taps do I really need? And the question can be answered with single pulse response. We can use single pulse response to identify the number of taps needed. And single pulse response is a technique that is more and more used in the industry, and I'm a big fan of it, is where we send a single pulse with a specific rise time and data rate, i.e. the unit interval, through a channel and see what comes out. And the single pulse response is very interesting because I haven't seen two of the single pulse response that are identical on the channels. It can help you identify the loss and impedance discontinuity. Now great, we have the single pulse response. How do we identify the number of taps needed? To do so, we will take a look at an example single pulse. Here I have numbered and separated them using unit intervals. These little marks, circular marks you see on the plot, is separated by 1 unit interval. Now if we name the maximum the cursor, whatever comes before it is the precursor. Whatever comes behind, after, is the postcursor. Having the knowledge, we can put it into decision feedback equalization, where when the received signal is coming in the plus sign, the summer, It goes through a symbol detector where the decision is made. And after this decision is made, there will be a feedback decision algorithm that goes back to the summer to correct what's happening. Now, one phrase I would like to add to advocate for the feedback decision algorithm is, if I detect a 1, I will emphasize the next 0. Likewise, if I detect a 0, I will emphasize the next 1. Well, in this case, since I'm seeing a 1 for this single pulse response, I could imagine the next 1, 2, 3, 4, 5, 6 tabs in the pulse cursor would be decreased. The level would be dropped to emphasize the next 0. Another way of looking at this is, say if we have another single pulse response where we have all 1s but 1 0, you will see if the algorithm is detecting a 0, the next 1 is emphasized. Namely, the level of the next 1 is going to be elevated. This slide shows how attenuated it is, the next 0. Like we said before, since the decision feedback equalization is sensing a 1, the next 0 is emphasized, the level is dropped. And if we put many of these single pulse response together, you will start seeing a little kink in the transition. And that is why this is a signature of DFE. And since the DFE is making a decision, the decision-making process itself, it is a non-linear process in terms of it's not 1 times 2 is 2, and then 2 times 2 is 4. It's not a linear response. A decision is not a linear response. And here we can look at how many tabs are there. I decided to put 6 tabs. We can see that the single pulse response can clearly tell us how many tabs we need, because after the cursor we have 1, 2, 3, 4, 5, 6 leakage in there, and I decided to put all of them in there. You'll see, however, since the last 3 are not major contributors of ISI, intersymbol interference, they won't improve the eye that much anymore. I would say that in this case, the first and the second will be the major tabs to take care of. Right, here we can see the detect 1 and emphasize the next 0. Well, let's see how it looks like in simulation. We have the closed eye, and we're going to add DFE to it. And here's how it looks like. We'll be expecting the signature kinks in DFE. And sure, there it is. In the transition area, we have the kink on the right-hand side of the plot. There is the kinks. That tells us we are using DFE to equalize. And comparing the left plot with the right, we can see that the closed eye is open, although a little skewed. Now to convince you, here is before equalization. The red curve shown here is without equalization, and I put a mask here for comparison, for scaling purposes. When I put on the same scale what has been equalized, and that is equalized eye with DFE. We can see that the mask that was totally outside of the non-equalized contour is now inside the equalized contour. Tell us that our equalization is working. That's our second solution. There's the third solution. Why not do both? I'm going to remove the stub and add the equalization to it and see how much better of an eye that we get. We're going to do remove stub and add equalization. Of course, we're going to expect the eye to open a little more a lot more actually, which looks like that. And again, the signature DFE kinks. And here's a contour to show the beginning, where without equalization, just removing the stub, we already have a pretty good eye opening. But to buy insurance, we can always add a little equalization to open up the eye even more. Now on the contour with equalization, it's totally covering up the mask. We're going to pass this test for sure. Next, after we troubleshoot, we went through this 3-step problem-solving technique for signal integrity problems. The next step is we're looking at an application pre-layout example with PCIe. And this is what you can do. We can end up with the setup on the left, where in the middle is a combination of all the vias and all the channels you have. On the left, you have crosstalk and transmitter, and on the right, you can place equalization as well. And also, we're going to talk about the back channel equalization in the upcoming slide. Just like in the problem-solving techniques, we use a modular approach. We take a look at one part at a time and keep adding on to it. We'll do the same thing with a pre-layout application example. In a pre-layout case study, usually you start with your transmission line and your substrate. And ADS is doing a good job of importing different board files. Then you will also include, if your substrate definition is also there, you can import the layout plus the net names and your substrate definition. And the first thing is to do for PCIe, the differential channel, we want to optimize it to 85 ohms. And our interconnect toolbox does just that. Our control impedance line designer, CILD, can help you quickly optimize for differential impedance, shown here. If you go to the optimize portion of the window, and you can optimize the width or spacing. After that, you'll be able to do a quick look of the loss at a given length. And here we have 0.2 dB at 1 inch, which is a little lossier than 0.1 dB per inch per gigahertz, but that's all right. That's just a quick overview that you can do. Next, once you have your channel, your differential channel, you'll move on to defining your differential via. And our via designer that comes with the interconnect toolbox is able to do a 3D full-wave analysis on this kind of via. We made the tool so that it's very easy to go from single into differential. And usually it doesn't take that long to simulate. Now, after you simulate the differential via, you want to put it back to the schematic and take a look at the channel simulation. That is okay. We have a generate circuit model symbol that will generate a layout lookalike to give you a better idea of what you're simulating in your channel simulation. Now next is the channel simulation, of course. First, again, we'll do rule number 9. We're transferring data in 8 gigatransfer per second. We'll use the same rule of thumb, 0.1 dB per inch per gigahertz. At the Nyquist, 4 gigahertz, I'm going to put in a 20-inch channel. Doing the math, 4 times 0.1 times 20, that's about 8 dB attenuation. And I would expect the eye to be somewhat open, but not totally open, which looks like this. And here is a case where loss might be your friend. On top here, since the eye diagram is showing me a little lossy, the eye is a little close, where the top and bottom are a little blocked off. That means where the crosstalk would happen, it would be masked. It would be masked by the loss here. And we'll see that in the next few slides. We have the transmission line done. Now let's add the via. Here's the transmission line, and I'm going to add the via lookalike right there. One going down, one leaving my transmission line. Learning from the previous example, this time I did back drill in my design. So I should expect the eye to look similar, to look really similar to what I've had before with only transmission lines. Indeed, it looks very alike, which confirms my belief that the stubs are removed. Next thing is, well, we have one differential pair. What if we have multiple lanes running in my PCI Express? That's great. It's all right. We can have 4 lines. They're all 20 inches. And we can add a little via for each of them. And now, since we have 2 channels, there might be channel-to-channel crosstalk. We can also model that in ADS. And like I mentioned, since this time around, the loss will be your friend. The crosstalk is switching. Another device is switching right next to your channel. But when it's switching, the quiet line will be at high or low, but it's masked by the loss. So I should, again, expect a similar eye. And there it is. This is the case where loss can be your friend. Although loss can be your friend, you still need the eye to be detected. So we will again add DFE. And after adding DFE, we'll expect the eye to be open, more open, and we'll see the signature kinks in the eye. And here it is. Eye is more open, and the kinks at close to 50 picosecond and 175 picoseconds. And that's DFE. That's a quick PCI Express layout example. Next, we will talk about what's happening between the TX and RX. We have the channel in the middle, and you have something leading to the channel, and some transmitter equalization. You have the FIR filter, and you have a pre-shoot with a TX-MI model. And it's connecting to the RX equalization. And one thing to note is to optimize the FIR taps, you really do need the channel impulse response. I.e., you need to know how many taps and what magnitude of the attenuation the tap is to use. And that's why in the upcoming, well, it's already out, the IBIS Summit, we have a auto negotiation where the TX gets to talk to the RX, and RX gets to talk to the TX to give TX the information about the channel, which is also, auto negotiation is also referred to the back channel interface, or there's a channel back to the transmitter. And after auto negotiation, the TX equalization is optimized for the channel at hand. And we'll see how that changed the eye. We started out with FIR taps, but not optimized through auto negotiation. And if auto negotiation is working, we should see the eye to be open since the FIR taps are optimized for the channel under test. Here it is. After auto negotiation, eye is open. And we're sure that our auto negotiation is working, and you can also use that in ADS 2017 Update 1. Great. We have finished quite a lot of content today, and here's a quick summary. First, we took a look at a case of the failing virtual channel, where we use the essential signal integrity analysis, such as eye diagram, mixed mode S parameter, single pulse response, and TDR to troubleshoot what's wrong with the channel. Next, we took a look at the PCI Express pre-layout example, where we built up layer by layer from our channel to via to crosstalk, and you can add on more to it. Say you have 16 lanes for your PCI Express, you will be able to model that and throw that into a channel simulation and include the crosstalk. And be sure to apply rule number 9 at every step so you know you're getting what you expect. Finally, I introduced the auto negotiation, aka the back-channel interface now available in ADS 2017 to optimize the TX equalization setup so that your eye is optimized. Well, if you want to have more of this great content, you'll be able to access it through a YouTube link. On the left-hand side of your console, there's a resource link to help you get a quick 10-minute version of the 3-step approach. And with that, there is a workspace to download as well that has all of these analysis in one place. All you need to provide is one differential S parameter, well, one single S parameter that has 4 ports. And after you click simulate, it will generate the eye diagram. Once you give it the data rate, it will generate the mixed mode S parameter and PDR and single pulse response. And after the single pulse response, you'll be able to play with. There is a interactive cursor selection tool where you decide how many tabs you want in your equalization. Having done that, you can go to another schematic and perform a channel simulation with the number you already selected. And more content is also available at Tim's Knowledge Center, where you can just Google Tim's Knowledge Center. And with that, I'll conclude my presentation. Thank you.
Hey, thanks, Tim. Wow, just a lot of one-stop shops. So thanks. As you know, Keysight holds many free webinars throughout the year, and we ask that you take a couple minutes to complete the survey. It's easy. It should be on the right hand of your screen. If not, there's a little widget on the side at the bottom that has a little clipboard. And here, a couple questions that we have is how would you rate your overall satisfaction with this webinar? If you want to go ahead and select a choice, that'll help us improve our webinars. And then our second question is if you have a need for Keysight Advanced Design System for signal integrity, and what would be your timeline? So please go ahead and answer that question for us. And then to help us understand your solution needs, please describe your application, or are there any other signal integrity solutions that you need help with? You let us know. And then any additional comments to us or to Tim. And again, as you're filling that out, folks can also go on to the question answer section. And if you have a question, you can simply enter in the question answer window. And Tim, I'm wondering, are you ready for your first question?
Yes, Carmina.
Okay, here's your first question. This is from Marco. I usually design transmission lines with Libra models. Does ADS have a Libra model?
Yes, ADS does have Libra model, but I do suggest you to use this control impedance line designer. Not because I'm selling you the tool, it's because Libra model uses an equation-based solver, meaning that it plugs in the numbers and gives you the result, which does not include conductor loss that precisely. So you do want to use control impedance line designer because it's doing a 2D cross-section using method of moments and solving the Green's function, and that's more accurate. Thank you, Marco.
Thanks, Kate. Tim, here is your second question, and this one's coming from Andrea. In the stub resonance example, why are you only showing the first reflection of the wave through the stub?
Great question. And well, the devil is in the details, but the reason why I show the first reflection is because that's a major contribution to the destructive interference. But I do have a workspace that shows, if you capture all of it, you do see the combined destructive interference. Thank you, Andrea.
Thanks. And then here's another question. This one comes from Monica. I'm working on a PAM4 design right now. Does ADS support PAM4?
The short answer is yes. And the longer answer is we do have PAM4 generic model, TX for IBIS AMI. And if you don't have a vendor to supply you with a model, we will happily help you with our generic model. Thank you.
Great, thanks. Thanks. I knew the answer to that one. So here's a question from Steve. Is your TDR differential or single channel?
It's differential. And if you download it, you can see that in the workspace. Thank you, Steve.
Thanks. And here's a question from Vivekanand. Thanks for asking this question. Is it usual practice to analyze DFE behavior with single pulse switching from 1 to 0? Also, are there any examples or experiment results that are available? And any examples or results that are available, please send on.
Yes, I do have a couple examples. And with that, you can try searching Tim's Blackboard on Google. You'll find it. And I would say it is a usual practice to analyze DFE behavior with single pulse response. And these days, to better understand it, you can also go from 0 to 1, 1 to 0, and that should just confirm what the algorithm is doing, right? If I detect a 1, I'm going to emphasize the next 0. Thank you.
Thanks. Another question. Can CTLE overcome discontinuities from vias?
Another good question. The reason why I picked DFE is since CTLE is a frequency domain approach, it really relies on the loss instead of a certain valley, certain dip of S21. That's why I picked DFE, since the dip is not happening across all frequencies. Instead, it's happening in a very specific frequency where the stop is resonating. I thought DFE will be a good way to use and to really educate people on using a single pulse response as well. Thank you.
Thanks. And here's a question from Keith, although this may have been answered already. How does the Nyquist frequency factor into signal integrity issues?
It is very important, since when you have a pattern, a data pattern, say PRBS, there's an underlying clock that is running by the Nyquist frequency. And once you have the Nyquist frequency, you'll be able to dissect this. You have the odd harmonics, and you want to use a Nyquist frequency as almost as a reference. If you are doing really well at the Nyquist, then you're pretty sure if nothing else is going wrong at the odd harmonics, you'll be doing fine in the eye. And that's the starting point usually.
Thank you. And then, let's see, this will most likely have a lot of questions rolling in, Tim. So, and I believe here was one. Oh, I believe you already answered this one from Armin. Do you have similar analysis for PAM4 single? You said that ADS does support it, but do you have a similar analysis for PAM4?
Not yet, but I'll be creating one for you.
Hey, that's nice.
Yeah.
All right. So Tim, I know that you are currently, rolling through these questions, but let's go ahead and close. But as we mentioned before, we will. Tim has promised to answer all these questions via email to you directly, and also today's presentation will email the link to the on-demand recording, and you can share that with your colleagues. And of course, you already have access to the copy of the slides and other resources. As Tim mentioned, his how-to video is only 10 minutes. It's application focused, and you get a free workspace. And you can also try ADS at any time. Just ask us for an evaluation. Tim, any closing comments before we finish?
I'm seeing a couple comments on not able to download, and I will fix that right away. Thank you.
Okay, great. Thanks, Tim. Thanks for attending a practical guide to signal integrity basic analyses and concepts brought to you by Keysight Technologies and the Signal Integrity Journal. Please visit us at www.keysight.com/find/events for a list of upcoming events. The copyright of the presentation materials is owned by Keysight Technologies. I'm Carmina. Thank you, Tim, and thanks for joining us today, and have a great day.
Hey, your towel is going, bro. My towel? Why you did this before, man? It's outside. Still, I have a clip. Mine things are there. Maybe,